All right, in this video, we're going to try to describe what happens with Hess's Law 2, which really isn't actually Hess's Law 2, it's just Hess's Law, but now we use it with formation enthalpies. This is in chapter 11.5, and the formula that we're going to use is here, which looks a bit daunting, but once we've used it a few times and understand what's going on, it hopefully will make sense. So these are using formation enthalpies. If I have carbon solid plus oxygen to make carbon dioxide gas, the data booklet gives us a molar enthalpy of formation of carbon dioxide of negative 393.5 kilojoules per mole. So the enthalpy of this reaction, which is a formation, is negative 393.5 kilojoules per the 1 mole. If instead we broke carbon dioxide gas apart and made carbon solid plus oxygen gas, the simple decomposition is going to be positive 393.5 kilojoule per 1 mole, which is to say that to break these bonds and make these bonds gives off this much energy, or breaking these bonds and making these bonds uses this much energy, because it's the same bonds being made and broken, but in opposites. We're going to end up with the same amount of energy. Well, think about the reaction. Any reaction that has reactants, so reactant compounds, are going to react. And if we could break them into elements, we're going to have a formation enthalpy, right, of this. The simple decomposition enthalpy of that. But then if I took those elements and made them into product compounds, this would be the change in formation enthalpy because we're taking the elements to make the products. So the relationship between the energy used to break bonds and make new bonds works if I can use just the formation enthalpies. So we'll apply that to the combustion of pentane. So if I have pentane and oxygen gas, I think pentane's a liquid. Pentane is a liquid, and oxygen gas to make carbon dioxide gas and water vapor. Because I know the formation enthalpies of all these chemicals, and I can balance the reaction, I can find the enthalpy of this reaction, so this is a combustion reaction, by taking the sum of the number of moles times the formation of the products minus the sum of the number of moles times the formation enthalpy of the reactants, which, because it's the negative, this is decomposing. This is breaking the bonds to become elements. So my enthalpy is going to be the coefficients of these. So I've got 5 mole times negative 393.5 kilojoule per mole. That's the molar enthalpy of formation of carbon dioxide, plus 6 mole times the formation enthalpy of water, which in my data booklet tells me it's negative 241.8 kilojoule per mole. So that's the energy of making these bonds from the elements, minus the energy to break apart the reactants. So it's going to be 1 mole of pentane times its formation enthalpy, which is negative 173.5 kilojoule per mole, plus 8 mole times the formation enthalpy of oxygen. Well, formation reactions make the element plus an element to make a compound, so it has an enthalpy change. But if it's the element becoming the element, the enthalpy change is going to be 0 because it's the same thing. There wasn't a change. So for every element the formation enthalpy to make an element is 0 kilojoule per mole. So I won't even bother putting that into my calculator. I'll show it in my calculation because it's complete. But if I sum this, 5 times this plus 6 times this minus 1 times this plus 8 times 0 gives me negative 3244.8 kilojoules. Now, all the moles are canceling out, right? So we don't end up having mole anywhere, but this is the enthalpy of this whole reaction. So my enthalpy for combustion of this reaction is negative 3224.8 kilojoules. If it then asks me what's the molar enthalpy of combustion of this, then I just do one more step. I just say, oh, for pentane, this is going to be negative 3244.8 kilojoules per 1 mole of pentane. And then that's the molar enthalpy. Right? So it's just a different communication standard. That's essentially how Hess's law works using formation enthalpies. You need a balanced reaction. You're going to take the sum of the number of moles from the coefficients times their formation enthalpies minus the number of moles times the formation enthalpies of the reactants, and you can calculate that way.